Welcome to the fifth episode of Iron. The title of today's episode is The Cost of Transactions. Last time what we did is that we took a path of a single message throughout the system. We look at how a request arrives at the message bus, how it is parsed there, then how it is moved to replica, where a request is transitioned to a prepare. The prepare is concurrently replicated using ring topology to other replicas and written to disk. And after it is written to disk and the primary receive the appropriate amount of confirmations from peer replicas, the primary goes and commits this prepare, which means that we actually execute the double entry accounting logic in the state machine. So what we're going to do today is, well, first of all, let me actually share my screen. I'm not showing anything yet, but well, I'm going to. Yeah, so what we're going to do today is to reflect on the shape of the code we've seen last week and understand why it is written in like this very weird way. And the keyword already was spoken today. The keyword is concurrency. So really, today we will look at how TrackDavidOl does concurrency and why it does it differently. So let's open our let's open terminal and let's try to open it on the correct screen. Go to TrackDavidOl. Now let's open our Iron. Okay, so concurrence, and to just give a short taste of that, remember that in replica, when we accept pair, here it is. So you see concurrency here. We replicate a message to other replicas. We write it to disk. Both of these methods, replicate and append, are non-blocking. So this means that they are happening at the same time. So okay, kind of like, why do we need to deal with concurrency? Because well, there is a good reason to not deal with concurrency, because like, concurrency is slow. not slow. Concurrency is hard. Like it is well known when you try to write a bit of concurrent code, testing the refinement is correct becomes much harder because with a linear algorithm, you just like run it on the specific input and you are done. It cannot behave any differently. Once you add concurrency into the mix, knowing just the inputs to the system isn't really enough because the ordering of how things happen while you process those inputs might, if your system is buggy, actually affect the results of the processing. So kind of like concurrency is hard. And the reason why we embrace concurrency, so let's add it as another guiding principle, embracing concurrency, is that we want to efficiently utilize the hardware we have because the shape of a problem is highly concurrent. And if we don't use all the underlying concurrency that is inherent to the problem itself, that means that we are running much slower than we could be otherwise. And kind of like this one is also kind of pretty big. And it's like fundamental. Well, it's not really fundamental. You could achieve reliability if you don't do concurrency within a process. So kind of like if you have a distributed system, you already have a concurrent system across different processes. But within the process, you could potentially write just like straightforward, like a single kind of like control flow threaded code. But this like lose a lot of performance. So this is like not fundamental for behavior of machines, but this is fundamental for performance. And let's just like try to map the concurrency we have. So first of all, if we look back at the message bus, what we see here is that we have many connections because in a cluster of 6 replicas, each replica communicates with 6 other peers, and this communication generally like doesn't need to be serialized. They are talking to each other on different port pairs on different TCP connections. Sorry, there is like some bug file around here. Yeah, so they're talking to each other on different TCP connections, and like this kind of like can be done concurrently. There's no need to block reading a message from one replica while messages from other replicas are ready. So one like source of concurrency is peer-to-peer communication between replicas. Related source of concurrency is communication with a lot of different clients. So again, even 6 replicas which form a cluster give a fair amount of like things going together at the same time. But there are also like thousands, hundreds of clients. Again, not like millions, because we have this API gateway system where the clients of Target are not like the mobile phones, but some machines in the cloud which aggregate underlying requests into batches of transactions. But still, you would like to run many of those API gateways potentially geographically distributed. So again, let me talk about it. I don't know, maybe hundreds of clients. Then, what we saw earlier today is that we have split between network and disk. So kind of like you have a network, you have disk, and you can run those two in parallel to each other. Though kind of like well, kind of like in parallel, but like really, we'll get into like concurrency versus parallelism. But well, anyway. And finally, disk itself can serve many concurrent IOs. So disk can accept many different concurrent write operations, and ideally you want to kind of like issue all those operations at the same time. Well, actually, kind of like this last one is like the main secret sauce behind Hagibit's performance, which we'll get to later when we'll get to LSM. But kind of like yes, we want to embrace concurrency here. So yeah, this is like quite a lot. But there is something else here. So let's say we want to like process something. Usually, like whatever your system is, whatever process is doing, it is like some series of stages. So input goes to stage A, goes to stage B, goes to stage C, and that is kind of like your result. And as always, you want to run those things faster. And kind of like the most like obvious way to run this faster, actually, let me do this effect. Like the most obvious way to run this faster is to do something embarrassingly parallel. So we take our input and we just guess the number of errors, and we kind of just split the input in independent chunks, in independent shards, and process each shard in parallel. And this is kind of like one common source of concurrency, of a very tame kind of concurrency, which is just parallelism. Because kind of like this situation is kind of like really easy. It is true that all those things happen concurrently, but the core thing is that not only they happen concurrently, they also happen independent of each other. And that actually means that like there is no real concurrency, because like if you don't talk to things which happen concurrently with you, that means that, well, they might as well not exist. This is like, in terms of like actual code, this situation is actually indistinguishable from a picture where like all those things run one after another, because again, there is like no communication. So kind of like concurrency is about things happening at the same time, but also about affecting each other in interesting ways, where like not only they physically happen in parallel, but it actually matters in which order things are happening. So this is kind of like standard picture of an embarrassingly parallel problem where you can just slice inputs and chunks. And this is the sweet spot. Like whenever you do like any kind of a compute intensive thing, you want to exploit these kinds of splitting the problem into pieces, because if you do this, then you could throw all your cores in it. Or like you could throw all your machines into it, because again, no one requires that these run on the same machine here, because they don't need to communicate. We can like distribute a thing in the cloud over there. So this is kind of like the sweet spot. And this is not something that Rust analyzers, sorry, I'm not longer working on Rust analyzers like Tagbittle. This is not something Tagbittle is doing. Actually, like Rationalizer does this. Like Rationalizer does embarrassingly parallel, but Tagbittle isn't like that. Okay, so and so let's actually try to add a title here. This is like embarrassingly parallel shape. I wonder if not knowing how to spend embarrassing is embarrassing. Embarrassingly parallel. Another thing you can do here is that you could do pipelining. So you could do something like this, where each thing, okay, and that needs to be like different inputs, 1, input 2, 3, 4. So this is like pipeline. So here, there is no actual kind of like concurrency of processing in the sense that like, let's say that like the C stage is like crucial and like each input is processed in order. When we get to stage C of the input 3, then stage C of input 1 and input 2 have already finished. So we see this result here, kind of like inputs might actually be interdependent between each other. But we still kind of like run more than one thing at a time. And we still can exploit more processing out of our hardware. But this is kind of like, this pipeline setup is kind of like last resort solution. You don't want to do this because the difference between those like embarrassingly parallel and pipeline situations is that the amount of concurrency you can extract from embarrassingly parallel task is unlimited. That's kind of like the definition of embarrassingly parallel. You can split it into how many chunks you want. So generally, kind of like if you have input, and if it's not like atomic like bytes, you can like split it in two. Sorry, I need to do a small pause here. Okay, I'm back, and we've actually tested the Redback site, so that's great. Okay, what are we talking about? Yeah, so you can do pipeline, you can do embarrassingly parallel things. Generally, you should always do embarrassingly parallel things because the amount of hardware you could throw at an embarrassingly parallel problem is, well, unlimited. Basically, like if your problem grows to be twice as large, you can just throw twice as many cores. With pipelining, this is much worse. In a pipeline, the kind of like amount of extra parallelism you can extract is limited by the shape of the code which does the processing. So if you have like 3 steps here, then you could run at most like 3 things in parallel. So kind of like you could not like push more things until the first one finishes. So yeah, but yeah, TidyBiddle kind of like is very much a pipeline, very much this thing, and not this thing. Why is that? And the reason for that is that kind of like, yeah, okay, let me maybe say one more thing here. So kind of like embarrassingly parallel is usually kind of like, sorry, embarrassingly parallel is really an aspect of a problem. Kind of like if your problem is embarrassingly parallel, if there's genuine independence between parts of the task, then it's great. And you just like code it up. While for pipelining architectures, kind of like we not so much speak about as like inherent parallelism and concurrency in the problem, as we speak about like parallelism in concurrency. So you have like specific code which solves this problem, and you like look for stages in this processing in this code which does processing which could be run concurrently. Okay, so why we are doing worse? Because the nature of TidyBiddle's domain, double entry accounting, isn't really well suited for embarrassing processing. So kind of like there's kind of like 23rd bullet point is that we do pipelining rather than, let's call it, data paralleling. And the reason for that is like, well, we need to do some of one of the two because we want to embrace concurrency, but we like have pipelining because we, there's a double entry accounting. Yeah, it's number 12. Because we do double entry accounting. So what is a transfer? Transfer goes from A to account B, and it like touches two accounts. So whenever like you like do like transfer, like you need to touch here and you need to touch here. And oh dear, okay. We'll maybe talk about the reusability later, but kind of like running a little bit ahead of us. When you have a bunch of transfers, you also want them to happen in a specific order. So to figure out whether like transfer goes through or whether there is like not enough funds in the account, you really need the ordering of all the transfers so that by the time you execute a transfer, you could actually say that, hey, like this account has like, this amount of money. So when you transfer funds between accounts, kind of like you might think that what you want to do is that you want to lock accounts and then shard your data across accounts. So kind of like we make the problem embarrassingly parallel by processing transactions for independent accounts independently. The problem is with like this direct solution that there are no independent accounts. Any two accounts could be linked by a transfer. And that means that we kind of like need to add locks to our embarrassingly parallel thing. And this might actually work. This might actually work in a world where like the source and destination transfers are completely random. That will probably spread out the workload pretty well. But there is a problem here. The curveball here is that accounts are uneven. Some accounts are way, way more popular than the other accounts. The usual picture is that there is kind of like a lot of accounts and they make transfers against like one big account, which is kind of like an exchange or a bank or something like this. So that means that actually when you start to add locks to the system, you don't get much parallelism because those popular accounts limit the inherent amount of parallelism which you could extract from the system. And what actually happens is that you do essentially sequential processing, but you also pay the communication synchronization costs of parallel solution. So you like take those logs, and then like you take log and you like process all the transactions under a single log because well there is like one account which accounts for like majority amount of transactions. So kind of like yes, the like, fundamental issue here is that it's hard to shard financial transactions. So what we do at Tiabilo is kind of like super like surprisingly simple solution. We just say that we are not going to deal with this problem at all, and we will just be running all our processing in a single thread. So kind of like actually, let me maybe rephrase this. So 23 would be like single thread processing because we have double entry accounting, which is like sharded and lock hostile. And it means that like we to like get out of limitations of single-threaded processing, we will be using pipeline. Okay, that's kind of like a big thing to say, and well, I'm not sure. I'm not sure that today's episode will be enough to cover everything. But let's please start. Okay, so kind of like that's a theory that we just going to funnel all the transactions through a single single thread, single place, which will be the synchronization point. So kind of like going through like this diagram that like B, that's okay. Let's maybe say that like A and C are like not important, but like B is like where we apply transactions. So B is like execute. And yeah, and those executes will run sequentially because we need two things. We need linearizable order of transactions and well, yeah, they have to execute sequentially because we need linearizable order of transactions. Let's, okay, sorry, I'm kind of like hard philosophical topic. I'm like running around in my thoughts because I have not prepared, but well, that's the genre of a talk. So actually, let's kind of like step back a little bit. And actually, let's add linearizability here. Linearizability. Okay, so I don't know how to spell this, but basically, when we track financial transactions, the semantics, I've actually talked about this, but let's just like put it down. The semantics we want from tracking financial transactions is as if everything happens sequentially, because only in this system you can say how much money is there in each account, and only in the system you can actually say, hey, is this transfer passive or not, for a reason understandable to a human. I think you could invent something or like some like transactions are kind of like genuinely concurrent, but that's going to be like super convoluted system, which would be hard for humans to reason about. So kind of like I guess because we want reliability, we want a simple model, and the simple model is linearizable. And so like B is actually, let's just like say it is like point of so our B is going to be like point of linearizability. That's like where like stuff happens in order. And there's like no locks because we are running on a single thread. But because we like don't do locks and like understand that, hey, this is kind of like a hot part, this could be like extremely well optimized. And for reference, here's the trick. So actually, it's not like A, B, C. You could actually make it like something like this. So the actual like, critical part, which has to be sequential, actually needs to be really, really, really tiny. It is just the act of executing the transactions. It's the only like the logic. Everything else, like networking, disk I/O, whatever, it doesn't have to be ordered. So the actual pipeline and target it all is going to look more like this, where like there is just one single phase which we run sequentially, but because we pipelined everything outside of this thing, can be pretty concurrent, pretty parallel. It can like reuse more of the resources, and this like sequential part can be like really tiny, really small. Okay, so I guess This roughly explains the overall architecture of Tiger Beetle in terms of like how we actually implement this. So let's recap this. We are doing financial transactions. Financial transactions are problematic because they involve pairs of accounts, and accounts tend to be very uneven. It is hard to parallelize financial transactions. Locks really force you to a single threaded execution. Instead, we say that we are going to process transactions in a single thread, but we are going to take advantage of the simplicity unlocked by the absence of locks, the pun intended, and we will squeeze every little bit of performance out of this sequential processing. Moreover, we try to make this sequential window as short and tight as possible so that the part which has to happen in specific serial order is kind of like really tiny. And to compensate for that presence of like fundamental sequential step in our process, which actually is required not by our implementation, but by the problem statement that we want transactions to be linearizable. So to kind of like overcome that, what we are going to do is that we are going to extract as much concurrency as possible from everything else. And that's what are we going to look at next. Okay, so how do we actually do concurrency? We live in the modern world, and in the modern world, the Linux kernel, and yeah, we kind of like actually, yeah, it's extremely important. So I think it's like unrelated, but we are pretty tied to Linux in particular because, well, kind of like we want to run reliably and fast, and Linux, by virtue of being kind of like the most widely deployed server operating system, is kind of like really well optimized. Well, I wouldn't say it's like really well optimized because, well, you obviously could do like much better if you have like super specific target. But it is like given the amount of hours spent on the Linux kernel, it's actually like doing extremely decent job. So again, we kind of like we want to embrace Linux. In recent years, Linux has like this IO uring thing, which is input-output user space ring buffer. So again, we like actually, well, I guess we could actually like flip those. We kind of like that kind of like the same because like, you cannot. Like, it's only really available on Linux at the moment. And the idea here is kind of like, it's really big. The idea behind IO ring is like not like I don't know. It's not a replacement for EPOL. Rather, it is a replacement for making systems calls. So traditionally, like when you do something like read or write as a syscall, what happens is that your process your thread issues a syscall, and then it blocks, it sleeps until the syscall returns. So it's kind of like this blocking API. And kind of like every syscall is kind of like blocking syscall. What Uring gives you is a generic ability to make, well, more or less every syscall concurrent. So that instead of like submit and wait, and then submit and wait, you actually do like submit, and then a single wait, which gives you all the results. And the way this is implemented, which is like inspired by L-Max Disruptor, is that there's like literally an in-memory ring buffer, which is shared between the kernel and the user space. So okay, kernel. kernel, and there's like user space. Also, I think kernel usually is drawn at the bottom. They kind of like have like this ring buffer. User space submits syscalls. And it has like a pointer to where it will place the next syscall. And the kernel has a pointer like where it is written those syscall, like the current syscall. And it's kind of like this, like you can imagine like this kind of like the two pointers race together. And this is kind of like a generic mechanism to exchange messages between two concurrent systems. And it could be really, really, really fast because there is like relatively little contention here. Because like the pointers like are like mostly independent. Like kernel works with like its side of the buffer, user space works with its side of the buffer, and under high load, when there is actually enough of like elements between those two, they don't contend on the same slots. There is only contention under light load. Okay, so this is kind of like the like really kind of like groundbreaking change in the interface to the operating system, because now like you kind of like you could write your entire application using kind of like this non-blocking message passing paradigm. You can like really want to embrace concurrency. That's actually like, again another reason why we want to use Linux, because we want to use IO Ring, because we want to embrace concurrency. And like IO Ring is like really great for the concurrencies. Okay, so let's actually look at how this physically works as a second part of today's episode, where we'll actually start looking at the kernel. Let's start with like something like message bus, our familiar message bus. Yeah, and let's look like what it takes to issue a receive syscall. So here is the call side, and here IO. No, it's not that IO. Okay, it's IO links. So here on the left, you could see the call side, and on the right is like the definition side. So how do we do kind of like syscall? Obviously, we pass the IO object. Then we pass the context type. And what is the context? Well, Zeek is a language without closures. So you gotta do closures yourself. And to do closures yourself, you need to pass an extra argument to each function, the environment. And the context is sort of like basically this extra argument. So we parse the context, which is just message bus itself. And then we pass the callback. And the callback will be receiving context as the first argument, which checks out again. Context here is pointed to a message bus, and here the first argument is pointer to the message bus. Then it will receive completion, and I actually don't understand why we need completion and what's there. So let's look. Oh, okay, so that's okay. That's not a pattern, but okay, let's for now like ignore it. So okay, completion, which is something, and then like actual result of the syscall. But that's callback. And yeah, we actually recently added a rule to our style guide, so the callback should go last, exactly for the reason that matches the execution order of things. So you should kind of like when you explain things, you say what happened in the callback class, because before we get to the callback, we actually need to cover. Let's do this so it's not confusing, you should actually like cover those things. So we can like pass completion and pass the actual circuit argument. So let's look at what's in the completion. Okay. It might have been a mistake to try to explain IO without actually prepping, because I understood that at one point, but I remember that this is kind of like not trivial, because what we see here actually is also this like a linked list of linked list, intrusive linked list of completions. Okay, and I'm confused here because there also should be a submission somewhere here. Do we have a submission here? No. Okay. Maybe I'm like mixing up completion and submissions. But okay, let's just try to just like brute forcefully dive into the code and understand what's happening here. So let's look at the completion argument. It plays two roles. Well, first of all, when again here we kind of like issue one syscall, but this happens for all of the different connections. And when our callback is called, when a particular receive completes, we need to figure out which completion are we talking about here, which connection are we talking about here. And completion is used for that using Zeek's idiomatic field parent pointer pattern. So connection, as a reminder, is an object which tracks a state of a particular connection. So for example, it holds, it should be holding a message somewhere. Yeah, it holds a bunch of, what's the send queue? Yeah, it holds a buffer of messages which should drain down this connection, and like also tracks like progress, like how many bytes we received of a particular message, how many bytes we parse, etc., etc. So that's kind of like this connection, and it holds this completion struct from our IO abstraction. And when a callback is called with a completion argument, you could find the connection related to this connection related to this completion by doing a field parent pointer. So to simplify, if you have some struct in Zeek, and you have a pointer to foo, somehow you got a pointer. You could get a pointer to S by doing something like field parent pointer as name of the field, and like a pointer to the field. So this is what happens here with connection. We know that this particular completion here is a completion embedded in a connection, because that's what we are passing here as an argument. Completion embedded in connection. So we could look back from this pointer and get the actual connection, then like process things. So this is like one of the purposes of this completion struct, like to be that breadcrumb from Hansel Gretel, which allows you to find your way back, allows you to find the original kind of like object which caused this callback to be issued. Okay, now let's look further, because here is like the very interesting aspect. So okay, what you see here is that this definition side of this IO abstraction and just goes and overrides the completion. And it overrides the completion with the data of IO operation which we are requesting. So the second purpose of this completion struct is holding the iteration, holding the arguments for what we are going to do. So we store the pointer to IO itself. We store the context and completion. Oh, actually, well, that's interesting because how could it work? Oh, nice. Well, not nice. That's actually like not a nice aspect of Zig because like sometimes when you're looking at generic code like this, you have no idea what's happening. But you see, so here we assign context to context, and context here is very non-confusingly of a context type, which is like very specific type, but actually it's like obviously pointer. We actually probably we should have done like something like this to like make sure that this is like clear that this is a pointer, and then here we actually say the context itself, but we are like passing the pointer. Well, anyway, it doesn't really matter. So this is a pointer, and here we assign it to the context. But this context is, well, it's essentially void star. So it's kind of type erased pointer to something. And this is like important line because it's not explicitly written here. But what happens here is that we have type erasure here. So it would probably be clearer if we oh, it's not any type, it's any opaque. It would have been clearer here if we explicitly cast here to underscore that this is where type erasure happens. And we do the same with the callback. Again, callback here is a generic function. It's parameterized by the type of a context. So different context type would give you different types of callback. Here we type erase it because in our completion structure, we want to have type erase pointer. The pointer type, which is like the same for all the operations we are going to submit, and operations are different again. So this completion is shared across receive, read, write, accept, everything. Everything goes for completion, so it has to have some amount of type erasure. So again, here is this type erasure. Zig doesn't have lambdas, so here like you actually, right? So this is like basically the Zig's way to define anonymous function. Zig doesn't have a syntax for defining anonymous function, so you define a struct, and then you take a function out of the struct. So here you see that like we can do type erasure in the opposite direction. Here we cast context to any opaque, and here we get any opaque as an argument. We cast it back to context, and we call, and then we call our callback, and then we specify the iteration. Again, this is kind of what I was talking about when I said that the completion supports all kinds of operations, which you could see here. Actually, well, I'm surprised that that's, wow, seriously, this is the entirety of the syscalls. We need to use a target on data play also. Accept, close, connect, read, receive, send, timeout, write, well, and read, and that's it. Not too many of them. And you see, like each thing here like stores the arguments of the syscall. So, for example, when we receive something, we need to give a socket, and the buffer where to write the data to. When we read something, we need a file descriptor, we need offset, like one important thing. When you use when you need an integer to define an offset in the data file, it always needs to be a U64 and not an usize, because disks might actually be larger than your RAM, and using a type which represents an address in RAM is not sufficient for pointing on data on disk. So like every offset always needs to be U64. Okay, so again, file descriptor, buffer, offset. Here is your read. Well, everything else is like, I guess, like pretty. It's like read is like read and write like the most complicated here because I have like 3 arguments. So okay, we specified operation here. So that's what happened. We have a receive call here, which is like type. This is a receive, and then we just go and like typeize it to like some syscall, so that we can show it to IOUA. Now let's look at this enqueue. This enqueue is kind of like pretty interesting. So one, so what does enqueue need to do? It wants to, okay, we don't have this. Where is, okay. enqueue wants to put stuff into this ring buffer, which is shared between kernel and user space. And this is like the happy case here. And we will cover the happy case, but let's start with the sad case. When there is no extra space here, we need to kind of like do something. Well, one thing which we could do is that we could say that, hey, this is called like immediately fails, which I think actually would be fine for Target because we have all kinds of retries internally, and like we expect syscalls to fail. But again, like, that's not great. Better, like the better strategy is like to try the syscall once you actually have space in the submission queue, and that means that we need to store like our syscall in progress somewhere and some user space buffer. And this is interesting. Again, this is topic for a future episode where we'll be talking about static memory allocation and how we have limits on everything. But well, I've already told you that we have static limits on everything. And that means that, hey, when we need to enqueue something because our queue overflowed, we cannot put it into some other queue because that other queue also might overflow. And we cannot just, allocate some buffer memory to put stuff in there because, well, we don't do dynamic memory allocation. So what are we going to do here? And this is reminiscent of amortizing analysis. This idea that, hey, kind of like if you want to do like this big iteration, you might actually want to like pay the cost of separation in installments. You might want to make every isolated chunk of work actually pay for itself. And here, because we already have this completion, we could actually use completion itself as a scribe space for these overflowing completions. And this is like what this is doing. We like use intrusive linked list here. So unqueued as the first in, first out intrusive queue. What's FIFO? Actually, I don't think I don't think I've read the code of FIFO just to understand from the name what it does. But yeah, so basically we have a type T, and this type T should have next field. Okay, so Linux. And like our completion indeed does have this next field. And then what this hyper will do is that it will like use this next to create an intrusive linked list of those things. So again, in Q, when the actual IOU ring shared between kernel and user space overflows, we kind of like enqueue this thing into user space Q. But user space Q is just an intrusive linked list, which uses the completion space itself, the space in the completion object itself. So that means that we kind of like can grow our queue of syscalls as long as we want to without actually doing any dynamic allocations, because we ask the caller to allocate that completion. And if we look at the message bus, IO completion is a part of a connection, and we allocate connections. Yeah, we allocate connections in the init method, and here we allocate a fixed number of connections. So let's say message bus allocated like 1,000 connections. That means that it allocated 1,000 completions, and those 1,000 completions would be used to store in progress completions from the message bus. Okay, so let's trace this more. Okay, so if we don't have space in this kernel buffer, we enqueue it. Otherwise, we like prepare, and prepare should be copying arguments of our syscall into the actual IOU ring. And that is handled by Zeek standard library. So I'm not sure if this okay, so this actually doesn't look like it calls the C library, and rather like it does synchronization itself. Yeah, so kind of like when you, so yeah, like the idea behind IOU ring is that there's like literally just like shared buffer between kernel and the user space, and you can just write. Usually, but this is like highly complicated lock-free data structure, so some like fancy synchronization is required. And usually people use lib IOU ring, the C library, to abstract this away, but it looks like Zeek just like does the thing manually. But like that doesn't really matter. What matters is that when we prepare receive, we actually go and write directly into the memory shared with the kernel. And that memory is pointed by SQE submission Q event and IOU ring. Yeah, and like IOU ring is well, it's still interesting. It's still our code. It's not a Zeek standard library. Get. Okay, here. Oh no, sorry, I missed. No, that's actually Zeek standard library. So you see like std here, and yeah, this is like this tricky atomic with the correct synchronization to like load the slot for submission event. Anyway, so okay, we're running out of time, but I think I will. Yeah, I think yeah. Let's make this one like a little bit longer, because I want to kind of like cover IOU ring in this session and like forget about this. So okay, let's go back here and what you're doing MQ. Yes. Yeah, but I'm not getting this. No, okay, sorry, yeah. Still mixed up which one is our solution STD, like ring is from standard library. Okay, so here I kind of like we just write that thing into the buffer. But we actually haven't we declared our intention to make a syscall, but we actually haven't kind of like submitted the thing, because that's kind of like the idea behind IOUing, is that you can enqueue a whole bunch of syscalls and then like submit them all at once. So we need to find the submit code, and the submit code is going to be driven from the main. So if you recall from like one of the earliest lections, we looked at this like 2-line main loop, and we have this like run for nanoseconds call here. And this is actually what makes the whole thing tick. So here we loop for this amount of time, which was specified. And if the queue is full, so we don't have any extra space for doing more syscalls, we flush submissions. And that's basically asks the kernel, hey, please actually take a look at this whole bunch of syscalls we submitted so far. And then we should be looking for completions. After we submitted our syscalls, we want to look at whether some of the syscalls have completed. So we get the completion events from ring buffer. And well, again, I probably should have said before this, but the thing about IOU ring is that it's not like a single ring to rule them all, because there's actually 2 rings. There is one ring for user space to kernel communication, and that is the ring of submissions. But then there is the opposite ring for communicating from kernel to the user space, and that is the ring of completions. And kind of like you want 2 rings, because bidirectional communication over shared buffer would incur like much more synchronization, as opposed to a situation where kind of like one side just reads and another side just writes. And if they want to flip, they have a separate area of memory with like separate synchronization. Okay, so let's see what happens here. So we get like some amount of completions, and so we get some amount of completions, and for each completion, we cast user data of this completion to our actual completion struct. It's actually okay, so let's go back to enqueue, because I think there is like one thing which I have not seen here. Because when we prepare, yes, this one. This is like, so remember when we did a receive call, there was like some bit of type erasure, because well, the caller has their own types, but we must convert them all to just single thing. Well, there is a second bit of type erasure happens here, because like IOU ring is like a single interface. It is used by many programs, and programs use IOU ring with like their own types. So there like needs, when program submits like its own callback with an iteration to IOU ring, it needs to somehow like type erase it. And type erasure happens through this user data field, where like when we submit completion, we set user data just a pointer to this completion. So then we is it? When we flash completions, when we like read completions, when we get completions from the kernel, we cast it back to the completion and push this to the completed queue here, not invoking callback immediately because something would be overflowing otherwise. Okay, where do we deal with this completed? Oh, right here. Well, are we not really doing anything here? Okay, so this is only for timers. We actually should be looking at Flash, which tries to do both. Yeah. So in Flash, we like send all the submissions we have so far. Then we get all the completions from the kernel, which we had, and that does not immediately involve callbacks from completions. That just enqueues them. So many comments. What is this? Okay, so I don't understand this bit. Maybe we'll come back to it later. There's the bit here. So we have this queue of completed things, and we complete every one of them. And complete means, okay, let's look at the completion of the receive. Complete means that we do some stupid retries related to Unix signaling out of scope here. The main thing here is kind of like we get results and then go and call the callback, which we'll call this type raised callback, which coming back to the message bus will be okay. Will be like our ORC function, which will like then do like some extra processing and may invoke thorough callbacks. Yeah, I guess let's stop it here. That was kind of like excruciating episode of Iron Beetle because we were like hand waving a lot and like discussing concurrency and all that stuff. The good news here is that we are going to be in this soup for the remainder of Iron Beetle show. So if it doesn't make any sense to you right now, that doesn't matter. Like you will learn just by watching more. But let's try to recap. So Iron Beetle, Target Beetle. The purpose of Target Beetle is tracking financial transactions fast and correctly. To track financial transactions correctly, we really want to create an illusion that they happen in a specific linear order. So that kind of like whatever concurrency we do internally, it shouldn't be observable from the outside. And tracking transactions, financial transactions specifically, or general transactions, is kind of a difficult task because transaction usually touches, or always touches two accounts. And some accounts are way more popular than others. So trying to shard across accounts and trying to lock individual accounts usually leads to poor performance. So the solution here is to actually run processing logic sequentially, but run it as fast as possible and try to minimize the extent of this like essentially sequential logic. This in turn requires Target Beetle to be kind of like highly concurrent. Again, that's kind of like the general theme in Target Beetle, that we kind of like pick something and this thing is hard, it's kind of a trade-off. And because we like pick this trade-off in this place which matters, we try to pick the opposite trade-off everywhere else. So again, we are a distributed system because we need availability. Distributed systems are hard So we aggressively pursue simplicity elsewhere for transactions. We run transaction processes sequentially. This limits the amount of parallelism, the amount of concurrency we have in our system. And for that reason, we actually minimize this fundamentally sequential extent of code and try to move as many things as possible to be concurrent and pipelined outside of this essentially sequential window. That means that we need to do a lot of concurrency. And the underlying technique we use to combat this concurrency is, well, IO during syscall from the modern Linuxes. And I think that's it for today. See you in a week, where we'll be, well, I don't know what we'll be covering next week, but I think I will remember at least half of the things which I forgot to explain in this lecture. So probably it's going to be concurrency part 2, Empire Strikes Back or whatever. Thanks you for watching, and see you relatively soon in just a week.